Okay, so we're recording for today. I have up here on the screen the things that you need to be working on for homework for tonight. So you've got some equilibrium homework, you've got some acid-base homework that you need to do. There's a lab on titrations that needs to be completed by tonight, plus a reminder about that extra credit lab that you want to be working on sometime before the end of the course. So when we look at our warm-up questions for the first one, we're told that we have a 0.200 molar acetic acid solution. Okay, we want to calculate the hydronium ion concentration and the pH. And it gives us the Ka for acetic acid. So you want to write down your acid ionization reaction, your ice chart, write a K expression, plug in your numbers, solve for hydronium, and then solve for pH. Okay, for our second problem, we're given 2.00 molar N2H4, which is our base. It's going to go through a basic ionization. We're going to produce hydroxide ions. Okay, we would write, again, an ice chart, write a Kb expression, plug in our numbers, solve for X. X will be hydroxide, figure out the POH, and then we can figure out the pH. So hopefully we have all that written down that we need, and I'm going to switch to my document camera and we're going to go over both of these problems. Let's see. Oops. All right, so let's take a look at that first question. So what we want to do first is we want to write out that equilibrium reaction. So we've got CH3, COOH, that's our acetic acid. It's going to react with water. Now, as a review, remember that acids donate hydrogen ions or protons, and bases accept them. So this proton here, this hydrogen ion, is going to go from the acid to the base. So when our acid loses its acidic proton, okay, or its hydrogen ion, it becomes the acetate ion. So acetic acid and acetate are a conjugate acid-base pair. When the water, which is acting like a base, accepts that proton, it becomes a hydronium ion. And the water and the hydronium ion are a conjugate acid-base pair. We have the arrow going in two directions because acetic acid is a weak acid. And we know that it's a weak acid, first of all, because it gives us a Ka value. Okay, so you're not going to have Ka values for strong acids. And we also know that there are only 6 strong acids. So hydrochloric, hydrobromic, hydroiodic, nitric, perchloric, sulfuric. Okay, so the arrow is going in two directions. We make our ice chart. So I is the initial concentrations, and it tells us in the question that we have 0.200 molar acetic acid initially. It doesn't mention the acetate or the hydronium, so there's 0 to begin with. Because it's a weak acid, only a small percentage of that acetic acid is actually going to react. So we're going to put minus X here, and X here, because the stoichiometry is a 1-to-1-to-1 ratio. So at equilibrium, we're going to have 0.200 minus X, X and X. But because this is a weak acid and such a small amount of this acid actually goes through this reaction, X is insignificant. So when we go to do our math on this, we're not going to include this X in our problem. Okay, we write our Ka expression. So it's the concentration of the products over the concentration of reactants raised to the power of the coefficient in the balanced equation. They're all ones. And we don't include water because water is a liquid. Remember that liquids and solids are not part of K expressions. We were given Ka. We know that we've got 0.200 minus X for our acetic acid, but the X is so small that it really is 0.200 in the end. And we've got X times X, which is X squared in our numerator. To solve for X, we'd have to multiply both sides by 0.200 and then take the square root, and that'll give us X, and X is the hydronium ion. If we take the negative log of that, that'll give us the pH of our solution. So what kinds of things do we want to talk about with respect to this first warm-up question? What kind of questions do you have? We all feel pretty good? And again, the more we show our work, the easier it will be when we add steps onto this today and then again tomorrow. All right, so let's look at that second question. Okay, for the second question, we have N2H4. Okay, it gives us a Kb value. So we know this is a base. We talked about how when we see this nitrogen in here, we know we're probably looking at something that's a base because it's going to accept those hydrogen ions onto the lone pairs of electrons. It's reacting with water. This time water is going to act like the acid. So the water is going to donate a hydrogen ion to our base. So the conjugate acid of our base is H2N5+, because we're adding an H+. And when the water acts like an acid and donates its hydrogen ion, what's left over is hydroxide. Because we're increasing the hydroxide ion, that's why this is a basic solution. Okay, the arrow is going in two directions because this reaction doesn't proceed to produce very much product before we reach equilibrium. Okay, we have our ice chart. So the initial concentration is 2.00, and there's nothing on the product side yet. Only a little bit of our base is actually going to go through this reaction, so minus X, and we're going to produce X and X. It's all stoichiometric, 1 to 1 to 1. So at equilibrium, our base is 2.00 minus X, but again, this X is going to be insignificant, so we're not going to include it. And we've got X and X for our products. We're going to write a Kb expression. It's written the same way the Ka expression is written. Okay, products over reactants, raised to the power of the coefficient in the balanced equation. Kb's will always have hydroxides in them. Kka's will have hydronium in them. We were given the Kb value, so 3.0 times 10 to the minus 6 equals X squared over 2.00 minus X. But again, because that X is insignificant, we're not going to put it in here. We multiply both sides by 2.00. That'll give us X squared. Take the square root of both sides, and that'll give us X. So X equals 2.4 times 10 to the minus 3. And that is the hydroxide ion concentration. So we can't figure out the pH directly from this number because it's not hydronium. But if we take the negative log of that number, that'll give us the POH. And when we subtract it from 15, then we'll get our pH. Okay, so we have just a little bit of an extra step in there in that we have to figure out the pH from the POH in the bottom of a weak base problem. So let's stop here. Anybody have any questions that you want to go over for how to solve these kinds of problems? They're not the kinds of things you're going to be seeing on your tests tomorrow. They'll be general equilibrium problems, but they won't be specifically about acids and bases until next week. All right, so let's stop sharing that. We'll go back to our original screen. All right. So let's take a look at some review questions. Okay, so we've got a couple of problems here. These are reactions that are at equilibrium. And then we do something to throw that equilibrium off. In the first set of questions, we're decreasing the volume. And we want to say which way is the equilibrium position going to shift. Okay, think about if we decrease the volume, what that does to the pressure. And then from there, what would happen to reestablish equilibrium? And then for our second problem, we're given some reactions that are at equilibrium. we're in some form told whether the reaction's endothermic or exothermic, we're going to decrease the temperature. And which way is it going to shift now? Okay, this is review for things you're going to see on your test tomorrow. I'll give you a couple minutes to go through all those, and then we'll do them one at a time and put the answers in the chat and see if we all agree. Did I say tomorrow? I'm sorry, Owen. The test is Wednesday. Did I say tomorrow? I apologize. Sometimes I don't know what day it is. All right, so let's take a look and see how we did. Let's look at the first question. If we decrease the volume, that's going to do what to the pressure? Just put it right into the chat. What would happen to the pressure if we decrease the volume? Is it going to go up or down? Good. Okay. The pressure is going to go up. Okay. So if the pressure goes up, the system is going to shift to the side that's going to decrease the pressure. So it's going to shift to the side with the smaller number of moles of gas. All right. So for A, which way is it going to shift, right or left? It's going to shift towards the left, right? We've got 3 moles of gas on the reactant side, 4 moles of gas on the product side. Shifting to the left will decrease the pressure and reestablish equilibrium. Excellent. Okay, let's look at B. Which way would it shift? Agreed, to the right. Now, this one's a little bit trickier. This solid we're not including. Remember that solids aren't affected by pressure changes. Plus they're not in K expressions. We have 4 moles of gas here. We've got 3 moles of gas on the product side. Shifting to the right will cause an increase in pressure, reestablishing equilibrium. Okay, so let's look at the last one, D. Or sorry, C. Where did D come from? C. Which way is it going to shift? Right or left? Okay, look at the states. I agree that we've got 2 moles on the reactant side and 2 moles on the product side, but carbon's not a gas. Okay, so that's just a little bit of maybe a trick. Just to make sure that we watch what the states of matter are. So we have 2 moles of gas on the reactant side, but we only have 1 mole of gas on the product side. So shifting to the right will increase the pressure and reestablish equilibrium. All right, so let's look at the ones that involve temperature. Okay, for A, is that an endothermic process or an exothermic process? The way that it's written. Good, it's exothermic. Energy's on the product side. Energy's being released. All right. So if we decrease the temperature, the system's going to shift to release energy in order to reestablish equilibrium. So for A, which way would it shift? To the right. Agreed. All right, let's look at B. Okay, written in a slightly different way. Instead of having the energy value right in the reaction, it's written over here on the side. Okay, delta H is 37.2. So is B endothermic or exothermic? Let's get some people typing in the chat. Is B endothermic or exothermic? It's endothermic, right? Delta H is positive. Okay, now, if we wanted to incorporate that, we would put it on the reactant side. So energy is considered to be like a reactant when it's endothermic. So if we decrease the temperature, which way is the system going to shift for B? Towards the left. Good. All right, let's look at C. Is it endothermic or exothermic? Exothermic. Good. It's a negative value this time. Excellent. I like all the participation. All right. So if it's exothermic, it's kind of like the way A was written. So energy is considered to be a product. Which way would the reaction shift if we decrease the temperature? Towards the right. Good. And then you could see towards products instead of saying towards the right. It's just another way of saying the same kind of thing. Okay. So we did have some questions and some issues on Le Chatelier's principle. So we did a little bit of review on it on Thursday, and we're doing a little bit more review today. Okay. Do we feel a little bit better now with how Le Chatelier's principle works with reestablishing equilibrium?
Yes, but could you maybe go over the first set, like B, and the first set of predictions really quick one more time?
B?
Yeah.
Sure.
That one.
Okay. So we're not going to include solids. Okay. We've got 4 moles of gas on the reactant side, and we have 1 here plus 2 here. We've got 3 moles of gas on the product side. Okay. Decreasing the volume increases the pressure. The system's going to want to relieve that pressure. It's what's going to want to reestablish equilibrium. So it's going to shift to the side with the least moles of gas. So it's going to shift, in this case, in B, towards the right.
Towards the, oh, okay. Yeah. I didn't realize the 4 in front of
oh yeah,
yeah.
Yep, there's a 4 here. Yep.
So I got a bit confused with that. Thank you.
You're welcome. Does that make sense now?
Yeah.
Good.
Could you explain why for C in part 2 shifts to the right?
Okay, so C in part 2 is essentially the same as A in part 2. Okay, it's just written in a different way. So whether we write the energy as a product or we say delta H is negative, it's exothermic. So the energy is on the product side. If we decrease the temperature, the system's going to shift to the side that releases energy. So it's going to shift towards the right.
Okay, so if it's exothermic, the energy is on the product side, and if it's endothermic, it's on the reactant side?
Agreed. Yep.
Okay, thank you.
You're welcome. And thank you guys for asking those questions, because I really want to help clarify things. If you don't ask me the questions, I don't know that you have them. So make sure that, we can always go over anything you want to go over. All right, my friends. So let's look at another problem. Okay, this is a basic equilibrium problem. Okay, so we have a reaction here. Okay, it's a generic reaction. We've got the arrow going in 2 directions. Okay, we're going to want to calculate, or first we want to write the equilibrium expression, right? The K expression. Then we want to calculate the equilibrium constants. And then if these are our new concentrations, is the system at equilibrium or not? And if it's not, which way is it going to shift? Again, these kinds of practice problems are great for you to do. And then we go over them. If you have any questions, it gives you the opportunity to ask questions on problems that you've worked on. So don't wait for me to do it and just copy it down. Okay, try it on your own. Okay, so when you write your equilibrium expression, it's products over reactants raised to the power of the coefficient in the balanced equation. Okay, that's the first thing you want to do. To calculate the equilibrium constant, to calculate K, you're given the equilibrium information. So you can fill that into your expression and calculate K. And then once you have K, you can take a set of concentrations and decide whether they're equilibrium values or not. And if they're not equilibrium values, then the system's either going to be shifting to the left or to the right to establish equilibrium. And I have the work kind of worked out, so I'm not going to put it up yet, but I agree with what Owen has there in the chat about what the equilibrium expression is. I would use a capital K instead of a lowercase k. Lowercase k is really a rate constant. Capital K is an equilibrium constant. They're related, but they're slightly different, but I totally agree with that. Now you're going to have to make an ice chart with this. Okay, you've got initial concentrations of hydrogen and iodine. You don't have any hydrogen iodide at initially, but it tells you how much you have at equilibrium. So you're going to be able to figure out how much you produced. You can figure out how much hydrogen and iodine reacted, and then you can figure out how much you have at equilibrium. Write that ice chart, though. It's a way to help you organize your information in your head. I'm going to change it real quick because I don't remember the answer. Somebody put it in the chat. Yeah, I'm getting 708 for my K value. Don't just take the numbers that I gave you there. Okay, figure out what X is, okay, which is the change in the hydrogen iodide. And then from that, look at the ratio. It's a 2-to-1 ratio for hydrogen to iodine. Then you can figure out your equilibrium values. And I'm going to go to the next slide just for a minute, and then I'll go back to this one because I worked the whole thing out. I apologize. Let's just look at the ice chart real quick. Okay. 1.43 is the initial hydrogen. 1.43 is the initial iodine. 0 is the hydrogen iodide. Okay. It's an X to 2X ratio. And HI is 2.66 at equilibrium. So 2X equals 2.66. That means X equals 1.33. And then you can figure everything else out to calculate your K expression. Okay, so I'm going to put that back and see if that helps a little bit. Because again, I think it's important for you to try and figure it out on your own as opposed to just copying down what I have. So hopefully showing you that ice chart kind of clarified what you needed to do.
Why do we not use 0.58 for the initial concentration of hydrogen iodide?
You're going to use this is a totally separate question. The third thing is a totally separate question. So you're going to calculate K first from this stuff. And then once you have K, it says, okay, here are a new set of concentrations. Okay, plug these into your Q expression, compare it to K, and decide whether you're at equilibrium. And if you're not, which way is it going to shift? So these numbers here on the bottom are a totally different question than these numbers up here on the top. Does it help?
Yes, thank you.
You're welcome. Again, I think I got, actually, why don't you put in the chat, what'd you get for the K value? I kind of had it up there, but I put it back. Anybody have the K value for the second question? Not yet. Okay, I think K should equal 708. And now that you know K, plug these numbers into your Q expression and see if it equals K. Okay, if K equals Q, you're at equilibrium. If it doesn't equal, K doesn't equal Q, then you're not at equilibrium. And Q needs to change so that it equals K. So which way would it shift? All right, so let's see. So we looked at our ice chart. Again, you were given 1.43 and 1.43 initially for your reactants. Product was 0. When it reacts, we don't know how much reacts, but X of the hydrogen, X of the iodine, and we're going to produce 2X of the hydrogen iodide. And it tells us at equilibrium, X or hydrogen iodide is 2.66. So if 2X equals 2.66, X equals 1.33. So what we can do now is we can figure out the equilibrium concentration for hydrogen and the equilibrium concentration from iodide. They're going to be the same, iodine. So 1.43 minus 1.33. So hydrogen and iodine at equilibrium are 0.10. Okay, our K expression, products over reactants, raised to the power of the coefficient in the valence equation. So 2.66 squared over, it's really 0.10 times 0.10. I just wrote it as 0.10 squared. Gives us 708. And there are no units for K. For the third question, since we don't know if we're at equilibrium or not, we're using Q. The expression is the same. There should be a square here. Sorry, that square got dropped somewhere. That should be there. So this expression here is the same as this expression here. And now we're going to put in the new numbers. So 0.58 squared divided by 0.81 and divided by 0.44 gives us 0.94. This number is nowhere near K. So the system's not at equilibrium. It's not even close. And then we have to figure out, well, is the reaction going to proceed in the forward direction to establish equilibrium, or is it going to proceed in the reverse direction to get to equilibrium? And we want to increase Q. Well, to increase Q, we want to increase product and decrease reactant. Shifting to the right will do that. Q will get bigger and bigger as the product concentration goes up and the reactant concentration goes down. And eventually Q will equal 708 and the system will be at equilibrium. Questions on that problem? It's a basic equilibrium problem, although the idea is the same as what we're going to be using in our acids and bases equilibrium that we're working on in this chapter. So if you have questions, I can clarify them. What kind of questions do you have? All right, so another thing that we did in the previous chapter is we related K, which is our equilibrium constant, to delta G, which is our free energy value. And we know how to relate delta G to K. Now, I'm going to remind you of what we need to do. So here's our equation. So K equals E to the negative delta G naught over RT. All right, now the R value you're going to use is 8.31, which is joules per mole Kelvin. Delta G is in terms of kilojoules per mole. So you're going to have to do a conversion here before you can plug it in here. And also, since this R value is in joules per mole Kelvin, we have to convert Celsius to Kelvin before we can put it in here. Calculate, this is the way I would do it math-wise. Calculate this whole exponent first, and then take E to that number, and that'll give you K. Let's see how you do. This was the last part of chapter 13 that we went over. Oops. Again, I only thought I did step by step, did the whole thing. Okay, so again, kilojoules per mole, we need to convert this to joules per mole before we plug it in here. Don't forget the negative sign too. R is going to be 8.31 joules per mole Kelvin, and 25 degrees Celsius is 298 Kelvin, which we want to plug in here. Figure out what this exponent is, take E to that number, and that'll give you K. All right, so that could just be rounding. Oh, maybe because I used 8.314, sorry. So I'm going to calculate this exponent first. So negative 25,700 joules per mole. I did a conversion so that this unit here and my unit in R cancel out. Okay, I think I said 8.31 and I used 8.314 here, sorry. And we want to use Kelvin here. So when we plug this all in, we're going to get a negative value for our exponent. So E to the negative 10.4 gives us 3.04 times 10 to the minus 5. The relationship between K and delta G. Everybody good? All right. So let's take a look at what we wrapped up class with last Thursday. So these are actually slides that we've already gone through, but I want to go over them again because this is probably the most difficult part of like acids and bases, is talking about salts, okay? Because it's not as clear whether they're acidic or basic. So we'll go through this and then we'll look at a couple of other examples, do some calculations and see how we do. And then we're going to move on to what are called buffers for today. So let's say we have a 0.100 molar solution of sodium cyanide. Well, sodium cyanide is NaCN. And it's an electrolyte. Okay, we know that any ionic compound that has sodium as its cation is going to break up into ions in solution. That's what an electrolyte is. So we start with that. Okay, we've got our sodium cyanide. It's going to break up into sodium ions and cyanide ions. Well, what we need to do next is look at the ions that are formed when this salt dissolves in water and decide which one of them is going to go through an ionization reaction with water. And in this case, it's going to be the cyanide ion, because the cyanide ion is the conjugate base of a weak acid. So now we're going to take this cyanide ion and we're going to react it with water. Now, the cyanide has to be a base. It doesn't have hydrogen in it. It couldn't even act like an acid if it wanted to. So it's going to accept a proton from the water. We're going to produce hydrocyanic acid and hydroxide. So we're looking at a basic salt. Okay. It's a salt that when it dissolves in water is going to increase the hydroxide ion concentration, which means it's basic. So once we have our reaction, we are just going to do the steps that we wrote before. What's the concentration? What's the K expression? Plug in the numbers and calculate the pH. So in this case, and I didn't write the whole ice chart here, just bits of it. So we've got 0.100 for our cyanide ion. It's really minus X, but the minus X is insignificant. And X amount of our hydrocyanic acid and X amount of our hydroxide. Now, because it's a base, we would write a KB expression. Okay, X squared over 0.100. And then we can solve for X. Okay, multiply, well, actually we were given, I didn't give it to you. If the Ka is 4.9 times 10 to the minus 10, if we divide that into kW, that'll give us Kb. So we know Kb, we're going to plug that in, multiply both sides by 0.100 and take the square root, and we get our hydroxide ion. If we know the hydroxide ion and we take the negative log of it, that'll give us the POH. And if we subtract it from 14, that'll give us the pH. So we're looking at a salt. When it dissolves in water, it increases the hydroxide ion concentration. So it's a basic salt. So our pH is going to be greater than 7. Now, we also looked at this at the end of class on Thursday. And again, we're just going to go through it again before we build on this. We have another salt, ammonium chloride. And when we put ammonium chloride into water, it's an electrolyte. It's going to break up into ammonium ions and chloride ions. And this time it's the ammonium ions that are the conjugate acid of a weak base, okay, of ammonia. The chloride isn't going to affect the pH. So we take our ammonium ions that are produced when the salt dissolves in water, react it with water. We're going to produce ammonia and hydronium ions. So ammonium chloride is a salt, but because it increases the hydronium ion concentration, it's an acidic salt. We're going to write a K, or we're going to fill in our numbers. So 0.100 X and X, write a Ka expression. Okay, we know the Kb for ammonia, we can look that up on a table. We can calculate the Ka for ammonium, plug it in here, multiply both sides by 0.100, take the square root of both sides, and we can figure out X, which is the hydronium ion. And once we know the hydronium ion, we can take the negative log of that, and that's going to give us our pH. So whereas acids are obviously acidic and bases are obviously basic, salts, we have to decide whether they're acidic or basic. And the salt's going to dissolve in water. We're going to look at the ions that are formed when that salt dissolves in the water and decide what's going to be affecting the pH of the solution. So let's look at another scenario. This is new. Let's say that we have sodium hydroxide and we react it with hydrochloric acid. Okay, well, it's a double displacement reaction. The sodium and the hydrogen would switch places. We'd produce sodium chloride and water. Now, sodium hydroxide is a strong base. It's an electrolyte. It's going to break up into ions. Hydrochloric acid is a strong acid. Okay, it's going to break up into ions. And sodium chloride is an electrolyte. It's going to break up into ions. So really, in this solution, we have sodium ions and hydroxide ions reacting with hydrogen ions and chloride ions to produce sodium ions, chloride ions, and water. Now, the sodium ions and the chloride ions are spectator ions. So when we look at this kind of reaction, really, it's going to be the hydrogen ions from the acid reacting with the hydroxide ions from the base to form water. When we look at sodium chloride, it contains sodium ions and chloride ions. Neither of those ions affect the acidity of the solution. So sodium chloride is a neutral salt. Sodium is the cation of a strong base. Chloride is the anion of a strong acid. And whenever that happens, the salt you're looking at is a neutral salt. So let's look at this scenario. We have 0.100 molar ammonium cyanide. Well, ammonium cyanide is a salt. It's going to break up into ammonium ions and cyanide ions. Well, here's the problem here. The ammonium ions are the conjugate acid of a weak base. So it will go through this hydrolysis process and produce hydronium ions. And cyanide is the conjugate base of a weak acid, so it will also go through this process and produce hydroxide ions. So how do we know whether it's acidic or basic? Well, what we have to do is we have to compare the Ka and the Kb values. If the Ka is larger than the Kb value, then it's going to be acidic. If the Kb value is larger than the Ka value, then it's going to be basic. And if the Ka value equals the Kb value, then it's going to be neutral. So if the Ka value is larger, the solution that's produced when that salt dissolves in water is going to be acidic because we're going to have more hydronium ions in the solution. And if the Kb is larger, it's going to be basic because we're going to produce more hydroxide ions. So it just depends. Is this equilibrium greater where we're producing more hydronium ions? It would be acidic. Or is this equilibrium producing more hydroxide ions? And then it would be basic. So salts are either going to be acidic salts if they increase the hydronium ion concentration. They're going to be basic salts if they increase the hydroxide ion concentration. They're going to be neutral if neither the cation nor the anion affects the pH of the solution. And both the cation and the anion can affect the pH, and we have to decide which one affects it to the larger degree. All right, so let's look at some practice problems. And we'll kind of do this step by step together. What is the pH of a 0.15 molar sodium nitrite solution at 25 degrees Celsius? The temperature doesn't have to do anything with this. And it tells us that the Ka for nitrous acid is 4.5 times 10 to the minus 4. And you're like, well, this isn't the same as this. True. It's going to give us a little bit of an indication about what to do with the problem though. Sodium nitrite is a salt. Okay, it's got sodium as its positive ion and nitrite as its negative ion. So what's going to happen is that sodium nitrite is going to break up into its ions. Okay, so sodium nitrite breaks up into sodium ions and nitrite ions. Now, sodium is the cation of a strong base. It's not going to affect the pH of the solution. Nitrite is the conjugate base of a weak acid. And since it's a conjugate base of a weak acid, it's going to go through a basic ionization reaction. So we want to write that reaction. We've got the nitrite reacting with water to produce nitrous acid and hydroxide ions. This is why it gives us that nitrous acid Ka value, okay, because it's in the reaction. Now, we need to decide whether or not this salt is acidic or basic. So look at this reaction here, specifically this. Is our salt acidic or basic? Put it into the chat there. Do you think the salt is going to be acidic or basic? We're increasing the hydroxide ion concentration. Okay, so it's going to be a basic salt. Agreed. Okay, we're increasing the hydroxide ion, which makes it basic. So that means we're going to need to write a Kb expression. We were given Ka. So we're going to have to figure out what Kb is. So for our Kb, it's products over reactants. And I didn't write the whole thing out here. I probably should have that there. So x squared over 0.15. Now we don't know Kb. The question gave us Ka. Remember that we can calculate Kb from a Ka value by taking Ka and dividing it into Kw. So Kb equals 2.2 times 10 to the minus 11. So this is what you're going to do on your own, and let's see if you can come up with the answer. This is Kb. We're going to plug it in here. So 2.2 times 10 to the minus 11 equals x squared over 0.15. Solve for x. Figure out what x means. And then calculate the pH of this salt solution. We did kind of the chemistry behind it. So now the math part of it should be something we can do. All right, so for hydroxide, which is what X equals, I have 1.8 times 10 to the minus 6. Since it's hydroxide, you're going to be figuring out the POH and then subtract it from 14 and figure out your pH. Plug it in the chat when you get it. Okay, it definitely should be greater than 7. I agree. Remember that if we have 2 significant digits in the concentration, we want 2 decimal places. So the pOH is 5.74. Subtract it from 14, and 8.26 is our pH. So we're looking at a basic solution, basic salt, because we're increasing the hydroxide ion. All right, let's look at another one. Okay, this time, hold on, my things are covering the question. All right, so we have 0.20 molar ammonium nitrate. And it gives us the Kb for ammonia. Again, a little bit of an indicator about what we're going to be doing with this salt. So the first thing we have to do is we have to write the dissociation of our salt, break it up into its ions. Think about what it breaks up into. It's ammonium nitrate. All right, so we've got ammonium nitrate is going to break up into ammonium ions and nitrate ions. Now, ammonium is the conjugate acid of a weak base. It's going to affect the pH of our solution. Nitrate is the anion of nitric acid, which is a strong acid. This is not going to affect the pH of the solution. It's not going to take hydrogen ions out of the solution because the hydrogen ions are not going to stick to the nitrate and make nitric acid. So we want to use the ammonium. And also they kind of gave us a little bit of an indicator about that here when they gave us the Kb. So the next thing we want to do is write down the acidic ionization for the ammonium. So we've got ammonium reacting with water. Remember that hydrogen ion is going to go from the ammonium to the water. We're going to produce ammonia and hydronium ions. All right. Because we did the last problem together, let's see, now that the kind of chemistry is written down there, let's see if we can follow through with the math. Since we're producing hydronium ions, we're looking at an acidic salt. We want to write a Ka expression because we've got hydronium here. Hydronium means Ka, hydroxide means Kb. So we're going to write a Ka expression, plug in our numbers. We're given Kb, we have to figure out Ka for our Ka expression. Calculate X. X in this case is hydronium. Calculate the pH. Let's see if you can do it. Again, since we've decided it's an acidic salt, when we calculate the pH, it should be less than 7. And again, when I typed these out, I was doing it, I guess, fast. I really should have the concentration of hydronium or ammonia times the concentration of hydronium divided by the concentration of ammonium before I do this part here. Kind of skipping some steps on the slide. It's a Ka expression. You have Kb given to you. You can calculate Ka from Kb. Okay, so I'm getting 5.56. That probably should just be 5.5. There's only 2 significant digits, or 5.6, sorry. 5.6 times 10 to the minus 10. Plug that in for Ka, solve for X. And when you solve for X, that's going to be hydronium. Figure out your pH. All right. I'm getting 1.1 times 10 to the minus 5 for the hydronium ion. Take the negative log of that, 4.98 for my pH. How'd we do? Sometimes the salts are the harder types of questions because you have to kind of figure out what's going through this second step before you can decide whether it's an acidic salt or a basic salt. All right. So now we're not really going to do so much math. We're just going to look at kind of relationships. So we want to arrange the following 1 molar solutions from lowest to highest pH. So think about that. Lowest pH means it has the highest hydrogen ion or hydronium ion concentration. Okay, it's the most acidic. Highest pH means it has the lowest hydronium ion concentration or the highest hydroxide ion concentration. So it's basic. So let's just look at these generally first. Well, hydrobromic acid is a strong acid. Sodium hydroxide is a strong base. Ammonium chloride is a salt. And since it has ammonium ions in it, it's an acidic salt. Sodium cyanide is a salt. And since it has cyanide ions in it, it's a basic salt. Ammonia is a weak base. Hydrocyanic acid is a weak acid. Sodium chloride is a salt, and it's a neutral salt. And hydrofluoric acid is a weak acid. So those are the kinds of things we have to think about. The strong acid is going to have the lowest pH. And the strong base is going to have the highest pH. Okay, so we know that this is going to be first and this is going to be last. The sodium chloride is a neutral salt. So that's going to be, somewhere in the middle. Sodium fluoride is an acid. It's just a weak acid. Okay, so it's going to be on the lower side of the pH scale. Hydrocyanic acid is a weak acid. It's going to be on the lower end of the pH scale. Ammonia is a weak base. It's going to be on the higher end of the pH scale. And then we have two salts. Okay, this is an acidic salt. This is a basic salt. So let's look at the acidic first. Okay, hydrobromic acid, hydrofluoric acid, hydrocyanic acid are all acids. Okay, they're all going to have low pHs. Now, the hydrobromic will have the lowest pH. If we look at the Ka values, hydrofluoric acid is a stronger acid than hydrocyanic acid. So hydrofluoric acid would have the next lowest pH. Hydrocyanic acid would be a little bit higher on the pH scale. And then ammonium chloride is an acidic salt. So it's going to have a pH less than 7, but it's going to be closer to 7 than the other ones are. So hydrobromic, hydrofluoric, hydrocyanic acid, and ammonium chloride. Now, when we look at the bases, sodium hydroxide is the strongest base, so it's going to have the highest pH. Ammonia is a weak base, so it's going to have a high pH, not as high as the strong base, but it's going to be higher than anything else. And then the sodium cyanide is a salt that is acidic in solution, so it's going to have a pH greater than 7. and then sodium chloride. So if we want to order them, hydrobromic acid would have the lowest pH, followed by hydrofluoric, which is a weak acid, followed by hydrocyanic acid, which is a weaker acid, followed by sodium chloride, which is neutral, followed by sodium cyanide, which is a basic salt, followed by ammonia, which is a weak base, and then finally sodium hydroxide, which is a strong base. So there's no math, it's just identifying what's an acid, is it a weak acid or a strong acid? What's a base, is it a weak base or a strong base? What's a salt, is it an acidic salt, a neutral salt, or a basic salt? Sorry. So it's just a little bit after 7. We're going to take a little bit of a break, and then we'll come back and we'll finish up about acids, and then we're going to look at buffers. So let's take about a 5-minute break. Let's come back at 7:10, and then we will finish this part up and then start talking about buffers. All right, get up, take a break, get a drink, go to the bathroom, whatever it is you need to do, and we'll come back in about 5 minutes. So what we're going to deal with next are what are called polyprotic acids. Okay, it literally means more than one acidic proton. Okay, and when we look at polyprotic acids, a good example might be phosphoric acid, H3PO4. And the reason is, if we were to look at phosphoric acid, it has 3 hydrogens in it, or 3 acidic protons. Well, when that acid reacts with water, only 1 acidic proton comes off of that acid at a time. So if we have phosphoric acid, the conjugate base of phosphoric acid is dihydrogen phosphate. So we're going to remove 1 hydrogen ion. It's going to join up with water. We're going to produce dihydrogen phosphate ions and hydronium ions. And the Ka value for this first step is 7.5 times 10 to the minus 3. But the conjugate base that's produced in the first step has hydrogen ions in it. It has acidic characteristics. So there's a second step in this acid ionization. So whereas the hydrogen or dihydrogen phosphate is the base in the first reaction, now it's going to act like an acid in the second reaction. It's going to lose another acidic proton to the water. Now we're going to produce hydrogen phosphate ions. Notice now the charge is -2 because we're losing a +1 charge. And more hydronium ions. But the Ka for the second step is much smaller than the Ka for the first step. And the reason for that is we're trying to remove a positive hydrogen ion from a negative ion. That hydrogen ion is going to be held more tightly in this acid than it was in the first acid. So this is a weaker acid than H3PO4. But again, if H2PO4, okay, dihydrogen phosphate is our acid, the conjugate base is hydrogen phosphate. And hydrogen phosphate also has a hydrogen ion in it. So we're actually looking at not just a polyprotic acid, this is specifically a triprotic acid because there are 3 acidic protons that can be removed. So if hydrogen phosphate is our acid, the conjugate base is phosphate. And notice that the Ka for that third step is even less than the Ka for the second step, because now we're trying to take a hydrogen ion away from something that has a -2 charge. And the phosphate that's produced in this third step doesn't have any acidic characteristics anymore. There's no hydrogen ions that can be removed. So we're done. It's a polyprotic acid though, because there's more than one acidic proton that can be removed, and they get removed one at a time. And the strength, the first step is much stronger than the second step, and the third step is the weakest. And this first step is not very strong. Okay, this is a weak acid. This is a weaker acid. This is the weakest out of the three. Now, there are several different polyprotic acids. We looked at phosphoric acid already. Okay, if we look at arsenic acid, it's a triprotic acid. It's got 3 acidic protons. There are 3 steps. And notice the Ka values get smaller and smaller as we go down. Carbonic acid is a diprotic acid. It has 2 steps. Sulfuric acid is diprotic, and it's actually unusual because the first acidic proton comes off 100%. Hydrogen or sulfuric acid to hydrogen sulfate is 100%. But when the hydrogen sulfate goes through that acid ionization, it only to a small percent carries out that second step. Sulfurous acid is diprotic, and hydrosulfuric acid is diprotic. Now, let's look at how these polyprotic acids are affected by their pH. So if we were to look again at phosphoric acid as our example. Okay, here's our acid ionization. The Ka equals 7.5 times 10 to the minus 3. Okay, we could say x squared over our concentration, and we could figure out what the hydronium ion concentration is. Okay, it's not here. We could do that, but we've worked on those kinds of problems already. So the hydronium ion concentration is 0.190. Now, if we were to look at the second step, the Ka for the second step is 6.2 times 10 to the minus 8. The hydronium ion concentration from the second step is significantly less than the first step. Okay, it's 10 to the minus 8, 0.0000000062. And if we were to look at the third step, now the hydronium ions that we're getting from the third step is even smaller than the second step. Now, overall, we are producing hydronium ions here, and we're producing hydronium ions here, and we're producing hydronium ions here. So the total number of hydronium ions is really the sum of the 3 steps, but with significant digits, it's really just the first step. The amount of hydronium ions we get from the second step and the amount we get from the third step are almost insignificant relative to how much we had at the beginning. So to calculate the pH, we would just need that first hydronium ion concentration. And the pH is 7 or 0.712. Again, we're getting a little bit of hydronium here. We're getting a little bit of hydronium here, but it's insignificant. It's not going to change the overall hydronium ion concentration, and it's not going to change the pH of the solution. So polyprotic acids. What we're going to do now is we're going to talk about buffers. We'll define what they are first. We'll look at how we can calculate the pH for buffer solutions, and then we're going to add acids and bases to buffers and see what happens. So when we talk about a buffer solution is a solution that has the ability to resist changes in pH when limited amount of acids and bases are added to them. A buffer solution contains a weak conjugate acid-base pair. And therefore, there's something for the acid to react with, and there's something for the base to react with in the buffer solution to neutralize that acid or base that's added. So if we just look at this picture here, okay, we have a buffer solution here, okay, has a pH of 8. And if we were to add hydrochloric acid to it, the pH really doesn't change. And there's an indicator in here that just shows us that the pH isn't changing. But if we have a buffer solution at a pH of 8, and we were to add a lot of acid, the buffer solution will eventually not be able to consume that acid anymore, and the pH is going to change. So let's calculate the pH of a buffer solution. So it says calculate the pH of an acetate buffer solution that contains 0.100 molar acetic acid and 0.12 molar sodium acetate. So the first thing we're going to do is we're going to write out our reaction. So we've got acetic acid, CH3COOH. Okay, you'd be given this. You don't need to memorize what that is. And we're reacting it with water. Okay, well, we know that acids donate their hydrogen ion. So the conjugate base of acetic acid is acetate ion. And the conjugate acid of water is hydronium. And we've got our arrow in 2 directions. Now, what's a little bit different about this kind of problem is that in our solution, we have acetic acid. Okay, we've got 0.100 molar acetic acid, but we also have acetate ions. So that means that our acetic acid is 0.100 minus X, because some of it's going to react. And the acetate ion comes from the sodium acetate. Okay, the sodium acetate completely dissociates. We have 0.12 acetate, and a little bit of it's going to react to establish equilibrium. And we're going to produce X amount of hydronium ion. Now, when we write our Ka expression, it's still products over reactants raised to the power of the coefficient in the balanced equation. So 0.20 or 0.120 minus X times X divided by 0.100 minus X. So we're figuring out that K expression the same way. Now, this is a weak acid. This is the conjugate base of a weak acid. So this is a weak base. That means this X and this X here are insignificant. Now, the Ka for acetic acid, you'd be given this, is 1.80 times 10 to the minus 5. This is a given. You look this up on a table. And now, because we're getting rid of this X here and this X here, 0.120 times X divided by 0.100. So we're going to multiply both sides by 0.100 and then divide both sides by 0.12, and that'll leave us with X. X equals 1.5 times 10 to the minus 5, and that's the hydronium ion concentration. We can calculate the pH. We take the negative log of the hydronium ion, and the pH of this buffered solution is 4.82. It's an acidic buffer. Now, there's another way that we can calculate the pH of a buffer solution, and it's by using what's called the Henderson-Hasselbalch equation. So let's say we have this generic acid, HA, reacting with water. Okay, the acid's going to donate its proton to the water, so we're going to produce A minus and hydronium ions. Okay, well, we know that the Ka expression are the products over the reactants. And we know that pH can be calculated by taking the negative log of the hydronium ion concentration. And if we were to take the Ka expression and kind of manipulate it a little bit to solve for the hydronium ion equals Ka times our acid over our base. All we're doing is solving for the hydronium ion by multiplying by the acid and dividing by the base. So what are we going to do with that from there? Well, the pH can be calculated by taking the negative log of the hydronium ion concentration. And that equals the negative log of the hydronium ion concentration. And because the hydronium ion concentration equals Ka times our acid over our base, we can do a substitution. So we're going to take this and we're going to substitute it in for hydronium here. Now, if we have the negative log of Ka times the concentration of the acid over the base, we can distribute the log into our parentheses, and it gives us the negative log of Ka plus the negative log of our base over our acid. Now, that simplifies this a little bit. And the negative log of the hydronium ion, that equals pH. And the negative log of Ka equals this new value that we're going to call pKa. And we have the log of our base over our acid. So this here is what we call our Henderson-Hasselbalch equation. If we know the Ka and we take the negative log of the Ka, we can figure out pKa. If we know the concentration of the base over the acid, we can calculate the pH of the solution. So let's look at another problem. It says calculate the pH of an acetate ion if we've got 0.10 molar acetic acid and 0.20 sodium acetate. That's the same question that we had before. But this time we want to calculate the Henderson-Hasselbalch using the Henderson-Hasselbalch equation. So we have our reaction. It's the same as before. But now, rather than writing a nice chart and writing a K expression and solving for X and taking the negative log of that, we're going to use this equation here. So pH equals pKa plus the log of our base over our acid. So for pKa, we would take the negative log of Ka. The negative log of Ka gives us the pKa value. We're going to add to that the log of the base concentration over the acid concentration. Well, the sodium acetate breaks up into acetate ions, and the acetate ions are the base in our buffer solution. So the 0.12 goes on top. The acetic acid is the acid in the buffer solution, so 0.10 on the bottom. And when we plug that all in, we get 4.824. It's the same number that we got in the previous math problem when we were solving for the pH of the solution. It's a shortcut of how to calculate the pH of a buffer. Okay, so make sure that you have that written down someplace. It makes life much easier than having to do a Ka expression in solving for X for buffer solutions. So let's look at another one. Okay, this time we have 0.25 molar ammonia. Ammonia is a weak base. And we have 0.40 molar ammonium chloride. Well, that's a salt. It breaks up into ammonium ions and chloride ions. And the ammonium ions are going to be the acid part of our buffer solution. And we're given the Kb for ammonia. We want to calculate the pH of the buffer solution. Well, the first thing we want to do is write down that reaction so we know the chemistry that's involved. So we have the ammonia reacting with the water. Since ammonia is a base, the hydrogen ions going from the water to the ammonia, we're going to produce ammonium and hydroxide. Okay. So we're going to use our Henderson-Hasselbalch equation. pH equals pKa plus the log of our base over our acid. So I'm going to kind of go through the steps and see if you can do the calculation on your own. So we need the pKa. We're given Kb, so we're going to have to figure out Ka. And if we take the negative log of Ka, that'll give us our pKa. So we'll have this part of our Henderson-Hasselbalch equation. We're going to add to that the log of the base over the acid. Well, the ammonia is the base, and the ammonium ion is the acid in our buffer solution. So we're going to plug in 0.25 here. We're going to plug in 0.40 here. And we're going to use the Henderson-Hasselbalch equation to calculate the pH of the solution. So see if you can do it. Calculate what the pH of this buffer solution will be. All right, so for the Ka, I have 5.6 times 10 to the minus 10. I'm just taking the Kb value and dividing it into Kw. All right, so the negative log of Ka will give me pKa, plus the log of the base, which is the ammonia, over the acid, which is the ammonium. And I get 9.05 for my pH for this buffer solution. Questions? All right. So we have a buffer solution, and let's say that this is our buffer solution here. Okay, we've got acetic acid reacting with water. We're producing hydronium ions and acetate ions. This is a buffer solution because it contains a weak conjugate acid-base pair. All right. Well, we know by definition, buffers resist changes in pH when limited amounts of acid and base are added to them. Well, how does that happen? Well, if we were to add an acid to this buffer solution, it would react with the base in the buffer solution and drive the equilibrium in this direction. And in doing so, the acetic acid concentration will go up and the acetate ion concentration will go down. If we have this buffer solution and we add a base to it, the base is going to react with the acid component of the buffer solution, and the reaction is going to go in this direction. And we're going to increase the acetate ion concentration and decrease the acetic acid concentration. So if we have a buffer solution and we add an acid to it, it's going to react with the base in the buffer. And if we have a buffer solution and we add a base to it, it's going to react with the acid in the buffer. So the reason why buffer solutions work is because they contain both a weak acid and a weak base that can react and consume the acid or the base that we add to them. So let's look at a question. Okay, so we have a 0.390 molar hydrocyanic acid solution that also has 0.350 sodium acetate. So I have a weak acid and a salt of its conjugate base. So I have a buffer solution. It gives me the Ka for hydrocyanic acid is 4.9 times 10 to the minus 10. I want to first calculate what the pH of this buffer solution is. And then I'm going to take the buffer solution and I'm going to add some concentrated hydrochloric acid to it. How is that going to affect the pH of the solution? So let's not do the second part of this problem first. Let's just calculate the pH of this buffer. It's going to be the same as the problems we just did. So use the Henderson-Hasselbalch equation. Okay, pH equals pKa plus the log of the base concentration over the acid concentration, and calculate the pH of the buffer solution. Okay, here's your Ka, calculate pKa. The cyanide in the solution is going to be the base, and the hydrocyanic acid in the buffer solution is going to be the acid. See if you can calculate the pH of the buffer solution. Don't worry about the second part yet. We'll do that part together. And when you get the pH of the buffer solution, put it into the chat first so that I know that you're done. And second, to see how we're doing and whether we have consensus on what the pH of the buffer solution is. So I'll give you a couple minutes. Let's see how you do. Okay, the negative log of Ka gives you pKa. Add to that the concentration of the base over the acid and calculate the pH. All right, let me know when you're done by putting some answers in the chat. All right, so let's see how we do. Looks good. We have some consensus here. Oops, here we go. All right. So here's our buffer solution. Okay. We've got our hydrocyanic acid reacting with water. We're producing cyanide and hydronium ion. Okay. This is our acid. This is our base. Okay. So pH equals pKa, which is the negative log of the Ka value, plus the log of the base over the acid. And I agree. Kind of just keep an eye on the significant digits. Again, you got three significant digits here, 3 decimals in your answer. All right. So now let's do the second part of this problem. We have this buffer solution. Okay, it's at equilibrium. The pH is 9.263. We're going to add an acid to this buffer solution. Well, acids react with bases. So the acid is going to react with the cyanide ions in our buffer solution. Acids react with bases. So the cyanide ion is going to react with the hydrochloric acid. Remember that hydrochloric acid is a strong acid. It breaks up into hydrogen ions and chloride ions 100%. Those hydrogen ions are going to be latching themselves onto water and they're making hydronium. So this comes from the hydrochloric acid that we're adding to our buffer. Acids react with bases. So the basic component of our buffer solution is going to be reacting. We're going to be decreasing the acid or the cyanide ion, and we're going to be increasing the hydrocyanic acid. Now, these are going to react stoichiometrically, and they're going to react to completion. So we have 0.350 moles of cyanide ion. We're adding 0.020 moles of our acid. And we have 0.390 moles of our hydrocyanic acid. The base in the buffer solution is going to completely consume the acid that we're adding to it. So the acid is the limiting reactant. All of the acid reacts. We want that arrow in one direction. Now, it's going to react in a stoichiometric ratio. So if 0.0200 moles of acid is reacting, it's going to react with 0.0200 moles of the base in the buffer. And it's going to produce 0.0200 moles of our acid. So once all of the acid has been consumed, the ratio of base to acid in the buffer solution has changed just a little bit. It's in a 1 liter solution, so the number of moles equals the molarity. So now we can calculate what the new pH is going to be after we add this acid to our buffer solution. So the negative log of the Ka gives us pKa. But now the values of our base and our acid have changed slightly because the buffer consumed the acid we added to it. So now the base is 0.330 and the acid is 0.410. So the pH does go down just a little bit, but it doesn't go down nearly as much as if we were to add that acid just to water. And that's what buffers do. Okay, now, it's a 1 liter container. It tells us that 1 liter solution. The volume here will cancel out with the volume here. We don't really have to put it in there, and in the future, we don't have to show it. Even if it's not a 1 liter solution, this volume number here will cancel out with this volume number here. So again, the pH decreased when we added the acid, but it only decreased by 0.047. It was 9.263. Now it's 9.216. So buffer solutions resist large changes in pH by either consuming the acid or the base that's added to them. So let's take that same buffer solution, and this time we're going to add sodium hydroxide to it. Well, sodium hydroxide is a base. It's a strong base. And the hydroxide ions from the sodium hydroxide are going to be consumed by the acid component in the buffer solution. Again, acids react with bases, bases react with acids. So let's look at what we have. We're adding sodium hydroxide to our buffer solution. The sodium hydroxide breaks up into sodium ions and hydroxide ions. The sodium ions are spectator ions. The base is going to react with the acid in the buffer solution. And strong acids and strong bases react to completion. So we're going to make another ice chart. Okay, our buffer solution was 0.390 moles in 1 liter. And the cyanide was 0.350 moles per 1 liter. And now we're adding a strong base to it. And again, that strong base, as long as we're within the limits of the buffer, is going to be completely consumed by the acid component in the buffer. So none of that sodium hydroxide will be, none of the hydroxide will be remaining. We've decreased the acid concentration in the buffer a little bit, and we've increased the base in the buffer solution by a little bit. So now we know Ka, we actually calculated pKa, so we really know pKa. We know the base, we know the acid, we can calculate the new pH. So the pKa plus the new concentration of the base over the acid. And this one actually is a little bit different because the concentration of the base and the acid in the buffer solution are equal to each other. 0.370 divided by 0.370 equals 1. And the log of 1 equals 0. So the pH equals the pKa. And we added a strong base to the buffer solution, but the pH, again, only went up marginally. It only went up by 0.047. And that's the function of a buffer solution. It will consume strong base or strong acid that's added to it. And it only changes the pH a little bit. All right, so let's look at kind of a comparison. Let's take some sodium hydroxide and add it to an unbuffered solution. Okay, that means that we don't have an acid in the solution to react with the sodium hydroxide. And it tells us that the unbuffered solution has a pH of 9.267. Well, the hydroxide ion concentration is going to be 0.0200. Okay, it comes from the sodium hydroxide. It's a 1-to-1 ratio. We want to calculate the hydroxide ion from the unbuffered solution. Well, we know the pH. And if we know the pH, we can calculate the pOH. And if we know the pOH, we can calculate the hydroxide ion that's in the unbuffered solution. So if we were to take the pH and subtract it from 14, that gives us the pOH. If we take 10 to the negative pOH, that'll give us the hydroxide ion concentration. Now, we have hydroxide from the sodium hydroxide, and we have hydroxide from the unbuffered solution we're adding it to. So the total hydroxide ion concentration is going to be the sum of the two. But 1.8 times 10 to the minus 5 is insignificant relative to 0.0200. So the hydroxide is coming from the sodium hydroxide, not from the unbuffered solution. So the pH is going to go from 9.263 up to 12.301. So the pH has a huge jump, a huge increase, because we're adding a strong base to an unbuffered solution. So buffered solutions resist changes in pH. Unbuffered solutions don't have components in them to consume the acid or the base we're adding to them, so there's going to be big changes in pH. Now, when we talk about buffers, buffers have a capacity. They can't take an infinite amount of acid or base and consume it. So buffers have the ability to prevent changes in pH within reason, as long as small amounts of acid or base is added to them. So the buffer capacity is the amount of acid or base that can be added without significantly changing the pH of the solution. So here we have a solution, okay, and it's got a pH of 8, and it's a buffer solution. And we add a little bit of acid to it, and the pH goes down a little bit. But the buffer resisted the change in pH because we were within the limits of the buffer. We were within the buffer capacity. But if we continue to add acid, eventually we will exceed the capacity of the buffer. And then any additional acid we add is going to really lower the pH of that solution. So buffers can't resist changes in pH forever, just within small quantities. And it depends on how much conjugate acid base are in the buffer solution to begin with. Okay, how do we prepare a buffer solution? Okay, well, we can use the Henderson-Hasselbalch equation to figure out how much base and acid we need to add in order to get to a particular pH. And if the base concentration is equal to the acid concentration, this ratio becomes 1. The log of 1 equals 0. So pH equals pKa. So when we look at a buffer solution, we want to have the concentrations of the acid and base in that buffer solution to be equal to each other, or at least to be close to each other. So when we go to choose which buffer solution we want to use, we want the pH to be as equal or as close to the pKa as possible. And we want the acid to base ratio in that buffer solution to be somewhere between 10 to 1. So let's say that we're given 3 possibilities for a buffer solution we want to make. We could make a buffer solution out of acetic acid and acetate ions. We could make a buffer solution between carbonic acid and hydrogen carbonate ions. Or we could make a buffer solution between hypochlorous acid and hypochlorite. And let's say we want to make a buffer solution that has a pH of 7.200. Well, which buffer solution is going to be the most effective? Well, what we want is the pair that's going to give us the pH or the pKa as close to the pH as possible. So we look up the Ka for acetic acid and the Ka for carbonic acid and the Ka for hypochlorous acid. And then we take the negative log of these numbers and we get our pKa values. So the pKa for acetic acid is 4.745. The pKa for carbonic acid is 6.367. And the pKa for hypochlorous acid is 7.456. Which one would be the best for making a buffer solution at a pH of 7.200? Well, this one's the closest to 7.200. So we would want to use hypochlorous acid and hypochlorite. All right, now we want to make a solution with a pH of 7.200. So I'll plug that in for our pH. The pKa is 7.456. And then plus the log of our base over our acid. All right, so how are we going to prepare our solution? Let's subtract 7.456 from both sides. That gives us negative 0.256 equals the log of our base over our acid. All right, well, we want to get rid of the log. So we'll just take 10 to the x on both sides. That cancels out our log. And we get 10 to the negative 2.56 equals the concentration of our base over our concentration of our acid. So if we plug this into the calculator, we get 0.555. Okay, well, what does that mean? It means the ratio of the concentration of the base to the concentration of the acid is 0.555 to 1. So if we wanted to make a buffer solution that has a pH of 7.200, we would need 1 molar hypochlorous acid combined with 0.555 molar hypochlorite ion. This would come from sodium hypochlorite, but the sodium is a spectator, so it doesn't matter. And if we mix these two solutions together, the pH of that buffer solution will be 7.200. Now, let's say that we wanted not the concentrations, but we wanted the masses. We're going to do the same kind of thing. Okay, this time we're going to use an acetate acetic acid combination because the pKa will be the closest to the pH we're looking for. Okay, and we can kind of ballpark this in our heads. If this was 1, the pKa would be 5. So this is going to be a little bit less than 5. All right, we're going to do the same kind of thing. We're going to use our Henderson-Hasselbalch equation. We're given the pH that we're looking for. We're given the Ka so we can calculate the pKa. Okay, so pH equals pKa plus the log of our base over our acid. pKa is calculated by taking the negative log of the Ka value equals the concentration of our base, which is the acetate ion, over our acid, which is acetic acid. Well, we know what pH we want. We want a 5.00 pH buffer solution. All right, what are we going to do now? We're going to subtract 4.75 from both sides. So 0.25 equals the log of our base over our acid. Okay, well, we want to get rid of the log function. So we're going to take 10 to the x on both sides. That gets rid of the log on the right-hand side of the equation and gives us 10 to the 0.25 on the right-hand side. We can plug this into the calculator and we get 1.78. That's the ratio of base to acid that would give us a pH of 5.00. But this time the question doesn't want to know what's the concentration. It wants to know what are the masses. Well, we know the concentration ratio, and we know we have a 1 liter solution, so we know the moles. And if we know the moles and we know the formulas, we can figure out the grams. So the mole ratio is going to be 1.78 base to 1 acid. Now, the acetate ions, where do they come from? Well, we can't just get a bottle of acetate ions from a stock room, but it can come from sodium acetate or any kind of salt that has acetate in it. Sodium is usually the kind of go-to cation that we use. So if we know the moles of the base, we can figure out the grams. There we go. So 1.78 moles of sodium acetate can be converted to grams by looking up the molar mass of CH3COONA. That's where that 82.03 comes from. Now we're going to do the same thing for the acetic acid. We have 1 mole. Here's our mole ratio because we're in a 1 liter solution and we're just converting moles to grams. 60.06 is the molar mass of acetic acid. So what does that mean? How would we make this solution? Well, if we took a 1 liter solution that contains 60.06 grams of acetic acid and 146 grams of sodium acetate mixed together, the pH of that buffer solution is 5.00. And then once we know the pH of the buffer solution, we can figure out if we were to add an acid or add a base, how would the pH of that buffer solution change? Would we be within the buffer capacity where there'd only be marginal changes? Or would we exceed the buffer capacity and then there would be big changes? So that's as far as we're going to go for today. I'm going to stop recording.